Today's lecture I will discuss on another MEMS sensor, that is inertial sensor, and this has got lot of applications. This is gyro sensors. Gyroscope is a well known device which is widely used in navigational purpose, and this particular sensor is used from from 18th century, even from there, but that time MEMS technology was not available, and people used the mechanical gyro, and which was bulky, and this sensors that time were expensive also. Each mechanical gyroscope cost is nearly starting from 10,000 US dollar to 1 lakh US dollar even in some cases. The major application there, those expensive and high precision mechanical gyros, are in case of inertial navigation systems, and in inertial navigation particularly what does it do, what is the basic purpose? They collect the heading information, and heading information of the aeroplanes, that is in avionics, missiles and satellites. So, those were the major areas we need such kind of sensors for getting the heading information and guided properly in proper direction. So, lot of research is going on since then, how to reduce the size and weight of those gyros. So, when the VLSI technology or integrated circuit technology is matured, then people try to use this technology to have such kind of mechanical structures, but that time MEMS technology or micromachined technology was not mature. So, after the 1980s, when bulk micromachining was standardized, then some of the devices came in the area of inertial MEMS sensors, and some devices were reported by analog devices in the gyro area, and this is basically the gyros are used to along with the accelerometers. Accelerometers, which I discussed in my last lecture, few lectures, that is for linear acceleration measurement, but gyros are basically meant for measurement of the rotation of any of the system, and the prices came down drastically when the MEMS gyros were reported. From say 10,000 US dollar, it has brought down the price nearly 1,000 US dollar. So, nowadays some of the gyros which are not that much critical and high precision, which are used in some toys also. So, Chinese people, they are producing a very low cost the gyros, that is of the order of say 100 US dollar only, and there are other applications of gyros which are not that much high precision. Those are in the area of automotive applications for ride stabilization and rollover detection. Consumer electronics applications are also there. One important application Japanese people are using, that is in their video camera, for video camera stabilized in camcorder, they are using the gyros, and those gyros cost nearly 100 US dollar per chip. Nowadays in many of the optical mouses for computers, they use also gyros, miniature gyros. Lot of applications are there in robotics, because in robotics there are a lot of movements, rotations are there in different parts of a robot, and you have to give the control movement of the parts with particular rotation. So, you need gyros there also, and above all nowadays there is a great demand of gyros for missile technology, which is basically the military applications, because in a guided missile, how much, in what acceleration it will move, and not only that, if you want to hit a target, then how much rotation, how much inclination you have to apply, so that it will take, it is a definite path to hit an object. So, that monitoring is necessary, then you need gyros also. So, those gyros are very crucial and high precision, they are called navigational grade gyros. These are highly expensive. These are the various applications of gyro sensors. Now, what basically gyroscope measures? It measures the change in orientation of an object. Silicon micromachined gyros are fabricated on the basis of coupled resonators. I will come into that topic later on, and they use vibrating mechanical element to sense rotation. So, basically it is a coupled resonators. There will be two systems, one for driving, another is for sensing. So, in that two system we have to have separate arrangement for resonating. Some vibration will be given to a particular parts or particular the electrodes, and then due to the rotation another force will be generated, that also will vibrate, and that is again you have to arrange for pickup of that vibration, which the resultant vibration is dependent on the rotation or angular velocity, angular movement of the system. The basic principle behind the gyros is transfer of energy between two vibrating resonators caused by Coriolis acceleration. The Coriolis acceleration is an important aspect in case of gyro action, and gyro design or gyro simulation. You have to know the Coriolis acceleration. This is basically an apparent acceleration that arises in a rotation reference frame and is proportional to the rate of rotation. That is the Coriolis acceleration. Coriolis acceleration, again I repeat, is an apparent acceleration that arises in a rotation reference frame and is proportional to the rate of rotation. Now, let us see what is the Coriolis force, how it is generated. In this diagram, the Coriolis effect is explained. If you see the diagram A, so there in a XYZ system, a particle which is moving along y direction with a velocity v. Okay. Now, if it moves with an acceleration, or there is a motion along v, there is a linear motion. Now, if you apply a rotation of the particle along z direction, this is a rotation rate, it is seen here, you can see here this is a rotation along z, this is omega, that angular velocity in which it is rotates along z axis. Then due to the interaction of the linear velocity v, a Coriolis acceleration will be developed, and that Coriolis acceleration is along the x direction, which is perpendicular to both y and the z direction, and that acceleration alpha Coriolis acceleration is equal to twice v cross omega. So, that is the basic idea of Coriolis acceleration, and this kind of acceleration can be very easily generated in tuning fork structure. So, in the B diagram, a tuning fork, vibrating tuning fork is shown. Now, here if you excite the two tines of the tuning fork, then these two tuning fork will vibrate in plane. you can see in this direction, that will in this direction. That is the normal tuning for vibration. If you hit one time, so then it will be some natural vibration along the plane of this tuning fork, in plane vibration. This will in this direction, that will in this direction. In tuning fork, natural vibration will be there. Now, if you rotate this tuning fork along the vertical axis, so this is shown by this circle, as a result of which a Coriolis acceleration will be developed, and because of that there is a force which will be generated, which is perpendicular to both the driving or in plane vibration and the rotation axis. That means that is shown because it is perpendicular in this direction, because you can see here, you can see that is the, you can see here. So, this direction is moving, this is in this direction, this is the out of plane motion. So, in plane is this one, this direction, and that is in this direction, that you are driving, you are applying. So, now you are rotating the tuning fork. So, because of that another vibration will start, that is in this direction. Okay. So, first vibration is in this direction. Now, you are rotating the thing, as a result of which the vibration will be generated, this is the out of plane vibration. Now, that vibration if you can pick up by certain means, and that vibration is dependent on the rotation, degree of rotation, is proportional directly to degree of rotation. Now, how much angle the tuning fork is rotating, so that can be measured with the help of this out of plane vibration. If you can pick up that vibration by some electronics, so that will give you the idea of the gyro or rotation. So, this is the basic mechanism of the vibratory gyroscope. Okay. Now, let us see now how this kind of gyroscopes are fabricated in MEMS technology or micro miniaturization manufacturing technology. Okay. Now, there are certain parameters of gyroscope. Let us define those parameters which are necessary when you pick up a particular device for certain application. Those parameters, obviously one is the resolution, and resolution of the gyro, it is expressed in terms of the standard deviation of equivalent rotation rate per square root of bandwidth of detection. That is definition of resolution in case of gyro. Standard deviation of equivalent rotation rate per square root of bandwidth of detection, degree per hour per root hertz. So, that is its unit. Another terminology is used in case of gyro, that is angle random walk. Basically, this is equivalent to resolution. A resolution is a common term which is used in many sensors that we know, but in particularly gyro, one terminology used, that is angle random walk. That is basically it's another terminology instead of the resolution, and its unit normally defined the degree per root hertz, degree per root hertz, sometimes degree per root h is written. So, that is the angle random walk. Another parameter is the scale factor. Scale factor of the gyro is defined as the amount of change in the output signal per unit change of rotation rate expressed in volt degree per second, that is the scale factor. The amount of change in output signal per unit change of rotation rate, okay, and is expressed in volt and degree per second. Now, other few terminologies are mentioned here. One is zero rate output or ZRO, and short or long term drift. What is ZRO? It represents the output of the device in the absence of a rotation rate. That is basically in normal sensor we call something as an offset. No input is given, but you get some output. So, here in gyro it is called ZRO or zero rate output. That means you are not giving any rotation, and even then if you get some output, so that is a ZRO or zero rate output. Another important terminology is a drift, that is short or long term drift. This is the peak to peak value of a slowly varying function which influences the output signal of a gyroscope in the absence of rotation. The short and long term drift means the performance changes with time. Even the same device, after calibration today, if you measure after say 1 year or 2 year, and you will find the calibration has changed. That means the whole thing has been changed. And what is the reason for that? That is why there is a function which is a slowly varying function, peak to peak value of the slowly varying function, that influences the output signal, and that is responsible for long or short term drift. Okay? And what is that function you have to identify. Gyroscopes are classified into 3 categories. One is inertial grade, second one is tactical grade, and third one is rate grade. 3 kinds of gyros are available: inertial grade, tactical grade, and rate grade. So, now the difference between this inertial grade, which is used basically for navigational purpose, and tactical grade are not that much high precision. So, their parameters are compared in this table. You can see angle random walk, which is basically the another terminology for resolution, degree per root hertz. In inertial grade is less than 0.001, tactical grade is 0.5 to 0.05, and rate gauge is greater than 0.5. Now, you can see the here inertial grade is resolution is very fine, less than 0.001. Bias drift degree per hertz is here is less than 0.01. In tactical grade is a 0.1 to 10, a rate gauge is 10 to 1000. Scale factor accuracy percentage, it is less than 0.001%, 0.01 to 0.1 and 0.121. Full scale range in case of inertial gauge is greater than 400, tactical is greater than 500, and rate gauge is 50 to 1000. So, now if you bandwidths are almost same 100 hertz in all cases. Now, if you see, if you compare the table, then you will find why the inertial grade, which is navigational, used for navigational purpose, is highly expensive, because these are very high precision gyros compared to the tactical and rate grade. So, rate grades are very crude. These are used in many of the household appliances, or in some cases of entertainment electronics is used. Tactical grade is little bit crucial, which is used for say automobile in other applications, but particularly for navigation means avionics, the missile technology, and as well as satellite application, there you require the inertial grade, which are highly expensive, because it is a very high precision. Now, the slide, next slide, we are showing here the silicon resonant gyroscope. This is an early example which works on the basis of coupled resonant principle, and here you can see there is a gyro element at the middle, which will basically rotate. This is the gyro element, it is shown here, and this can rotate. Now, as per the vibrating gyro principle, what we mentioned earlier, you have to have an arrangement for driving some of the electrodes for vibration. So, here the vibratory drive axis is here. So, here the energy you give is the electrostatic energy for movement of that. By electrostatic you can give, piezoelectric you can give. So, different kind of the transduction mechanism you can adopt. In silicon you can have to have piezo, that is in piezoelectric can be used in case of quartz, but here you can give the electrostatic drive. So, by electrostatic drive you give a movement of this particular electrode here and here, in the both the cases you can see here and here you give that. So, there is a vibration of that. Okay. Now, in the middle there is this is a gyro element, which if you rotate, input rotation rate is omega, if you rotate here this along z axis. So, as per that rotation gyro principle, the Coriolis acceleration will be developed along this axis. So, that is the vibratory output axis, it is called vibratory output axis, and these are the electrode, this one and this one. So, now a initial vibration has been initiated along this axis. Now, because of the rotation of this element, so another vibration will be developed along this axis, this vibration, say this electrode will vibrate. Now, this vibration you have to take it out. So, that vibration is dependent on the rotation along this z axis. So, that is the basic principle of silicon resonant gyros. But as we have seen, the structure is highly complicated. So, different elements has to be fabricated and it has to be coupled and fixed in proper manner, so that it can pick up the rotation. The important is this rotation should be directly proportional to the output vibratory axis for a fixed value of drive energy. So, that is the silicon resonant gyroscope basic thing. Then another class of gyro which are used later on, so that is micromachined ring gyroscope. So, a very popular gyro in the beginning of 19th century was used, that was not MEMS based, that is ring laser gyro. What was that? So, in a ring laser gyro, two laser beams were guided in a circular path in opposite mode. So, those laser beams will interfere each other, and if you rotate the system, the laser which is guided through the fiber optics, and if you rotate the total system, then interference pattern will change, and from the interference pattern you can get some idea about the rotation of that total system. That is known as a ring laser gyro. For a long time before the MEMS gyro came into the picture, people used these ring laser gyro. This is also high precision and not that much bulky as the mechanical gyros. So, some kind of similar principle is used in some form of MEMS structure, which is formed by electroforming of nickel into a thin polyimide mold on a silicon substrate. So, this is a rotation system is there, and here the nickel electroforming plates are there. So, there some of the energy, whether in a this structure is ring like. So, here is a not laser, but some form of electromagnetic energy is this circulated, and some interaction will be there due to the rotation of these wheels, and that may be reflected back. So, that is some form of a ring gyro, but that is not that much popular. Here one complete microsystem is shown in this picture. So, which is a rate sensor with a single chip rate sensor, and it works with 5 volt supply, 150 degree per second is its resolution, self test 0.03 degree per second per square root of hertz and 5% compensated is the analog device. So, here the along with the gyro, the peripheral, the electronic circuits are all integrated inside the chip. So, is a complete the you can say the smart gyro sensor, because the sensing and electronics part all are together integrated. So, it is from analog device. Another picture I am showing, it is reported by some Japanese group, and it has been reported in 97 in some workshop, IEEE MEMS workshop. This is a gyro with CUM drive, and that is fabricated using the surface micromachining technology, and its resolution here is 0.1 degree per second at 2 hertz, bandwidth is 100 hertz, the linearity 1% full scale in a range of 90 degree per second. So, this is basically CUM drive polysilicon gyro and Z axis vibratory, Z axis rotation axis it can sense. Okay. So, that is a CUM drive. Now, I will discuss little bit in detail the vibrating gyro tuning fork type, which is developed in our laboratory also using Quartz micromachining technology. In tuning fork, the tines are differentially resonated to a fixed amplitude. When rotated, the Coriolis force causes a differential sinusoidal force to develop on the individual tines orthogonal to the main vibration. This force is detected as differential bending of the tuning fork stem. I will discuss with the diagram in the next slide. So, the tines are drives and sensed into resonance by electrostatic, electromagnetic or piezoelectric mechanism. In microgyroscope, the Coriolis force, this Fc is given by k into v cross omega. K is a constant, v is the velocity, omega is the angular velocity, which is shown in earlier diagram also. Maximum sensitivity of the microgyroscope occurs when the frequencies of vibration due to actuation and Coriolis force are nearly equal. Now, what are the technologies used for vibrating gyro? They are silicon bulk micromachining and wafer bonding technology, polysilicon surface micromachining, which is the CUM like gyros, metal electroforming and Liga process is also used. Combined bulk surface micromachinings are used nowadays with some typical type of the high precision gyros. So, here is one kind of gyro, which is dual tuning fork gyro chip. This has been designed in our lab and we have also fabricated that. Here, let me explain this particular structure, how it works. Now, here you can see is a dual tuning fork, one tuning fork at the top and another tuning fork in the bottom. They are connected by a stem. So, now this dual tuning fork is supported by a ultra thin suspension bridge. You can see this is ultra thin suspension bridge here and here. This particular bridge thickness is very small, but its width is large. Now, this bridge is fixed with a support. These are the two supports, and these two supports, with this help of this support, the whole structure is fixed. Now, let us try to understand how it works. Now, the upper tines of the tuning fork is called drive tines. That means that some driving energy for driving force we have to generate here. If you make this particular gyro using quartz, then quartz is a piezoelectric material. So, if you apply electrical voltage along the surface of this material, so it will vibrate to its resonance frequency because it is a piezoelectric material. So, now here through electrodes we connected some source and you can control that source to drive the tines at a particular frequency. Now, if we apply some driving force, some voltage here, the tines will vibrate in this direction, out of plane direction. You see here it is shown in this diagram. So, these two tines will vibrate in this direction, in plane vibration. Now, what will happen? This support is fixed. Now, you try to rotate it. If you rotate it, then as I mentioned earlier, a force will be generated which is out of plane. That means this is in this direction, this because these two tines will vibrate, one in this direction, this one in this direction. Now, this vibration, how do you pick up, how you transmit? Then those vibration, if you want to sense, then you have to pick that vibration in other tuning fork. Because here there are two vibration, one is in plane, another is out of plane. So, they will couple, but from there you have to take only the out of plane vibration, and that transferring the vibration to the lower tines is a challenge. How can you do it? Let us see here the bridge, the micro bridge which is formed here, that thickness of the micro bridge in the vertical direction, that is thickness is very small, but the in plane vibration which is in this direction to this direction along x direction, okay, that thickness you see is a long and width is small. So, that means because of the support beam, so that vibration cannot be transmitted into this, but the out of plane vibration can easily be transmitted to the lower tines because the thickness here of this bridge is very thin, small. So, this vibration which is in this direction, that will be transmitted easily through the micro bridge to the down tuning fork. So, down tuning fork will selectively respond to the out of plane vibration, and then it started vibrating in this direction, what is shown, and because of that vibration, what will happen? EMF will be generated because it is a piezoelectric material. Because of the vibrations, some EMF will be generated at the surface of the electrodes. So, those field which is generated because of the piezoelectric effect is amplified in an amplifier, and that is then sent to a detector and you can detect the signal. Now, how much the lower tines will vibrate? It depends on how much the Coriolis acceleration is generated, and it depends on how much rotation you are giving to this system. So, that means the output voltage which is obtained from the lower tines is directly proportional to the rotation. In this way, using the piezoelectric drive, you can easily get the micromachine gyro using quartz micromachining. So, this kind of gyro has been designed and fabricated using quartz micromachining technology in our MEMS laboratory. So, now here we use Z-cut quartz crystal plates of 500 micrometer thick. The miniature dual tuning forks formed by micromachining, photolithography, anisotropic etching of quartz, and the resonance frequency of the structure which you have designed is 40 kilohertz, natural resonance frequency of that. Every tuning fork is having some resonance frequency, natural frequency of the structure, and it is dimension is this 11 millimeter, 12 millimeter and 0.5 millimeter. Okay, length, width and thickness. Upper tines are used for piezoelectric driving for in plane vibration. Just now I mentioned upper tines. lower tines for sensing out of plane vibrations due to Coriolis force, senses rotation speed. These are the highlight of that particular structure. Okay. Now, here again the vibrating being tuning fork, how it works, that is also shown, is basically you can see this kind of structure can be used for acceleration purpose also with certain modification. Here is again it is shown that the u naught sin omega t and minus u naught sin omega t. So, if you heat a tuning fork, it will always vibrate out of in this kind of thing, is not it? So, it will vibrate in this way. So, that is one displacement is u naught, another is minus u naught from there. So, this because of that, now the tuning fork is rotation here, torsion is given and torsion is with angular velocity omega, then it is shown the one is the perpendicular in the bottom line and another is a perpendicular in the top, there is a plus Fc and minus Fc. So, that is shown, one is minus Fc, another is a plus Fc dot, dot means a perpendicular to the structure, that force will be generated. Okay. That is the basic principle of vibrating tuning fork. Now, displacement due to the vibration along x axis is u2, that is a displacement is u naught y sin of omega t. Coriolis force on a mass element dm at y is given by twice dm omega u naught y omega cos omega t along z axis, and that Fc which is generated is proportional to velocity into angular momentum. I told you earlier also. The Fc which is shown in earlier diagram produces out of plane vibrations proportional to omega Fc. A driver transducer induces in plane vibration, a sensing transducer picks up out of plane vibration proportional to angle of rotation. That is the whole the design calculations or the principle is narrated in this slide. Now, the thing comes into our mind, how you go for the electrodes. This is again a real challenge, because the driving the tines depends on how the electrical energy is feeding into the tuning fork structure, tuning fork tines. And on the other hand, the sensing tines will sense the vibration and that vibration will be picked up by the electrodes in the form of voltage. How will you form the electrodes there? It has been observed that the efficient, the sensing, pickup of sensing and efficient driving is possible to a piezoelectric material with an optimum design of the electrodes, and that is shown here, and we have simulated by driving in different driving the electrode with different electrode geometry, and it has been shown that for driving, if you apply positive here and here, the top and bottom you can see in this diagram, and negative in the side wall, then the maximum easily you can drive the tines with maximum efficiency with no loss of energy. But here the problem you can foresee that you are making the electrodes in the all the four planes. So, you can make electrode in the top plane in evaporation and then lithography. You can make electrode in the bottom plane also by reverting back to the surface top side bottom. But how do you make the electrodes at the side walls? That is a very difficult situation. So, then some people are proposing that this structure can be modified to that, where the positive electrodes are here and in the both the side two negative electrodes are there. Similarly, in the bottom also positive at the center and both the side two negative electrodes are there. Now, if you connect the positive and negative like this, so it will be efficiently driven and maximum energy will be transferred to the tines. So, that means it is a planar. top and bottom both the plane you can make the electrodes like that. Electrode means the metal strips which is connected to the power supply. Okay. For sensing similarly, that means bottom tines, lower tines of the double tuning fork. So, then the electrode patterns like plus and minus, here minus plus, because this is out of plane vibration. So, that you can, if you make the electrode design in this fashion, the pickup signal will be efficiently picked up from the sensing tines. So, now this kind of the electrodes has to be formed on both the tuning fork lower and bottom tines, which is not very simple even if you modify the planar also. Okay. Now, some simulation has been made and rotation speed or natural frequency with the deflection of the tine, because tines will be deflected if you change the speed of rotation, then the because of the transfer of the energy correlates acceleration to the lower tines. So, it will be its vibration will change and its frequency also will change. So, that has been simulated and it is plotted here. One is x amplitude per tine length and another is y amplitude per tine length. In the other curve shows the rotation velocity or natural frequency versus the deflection of the tines for the with flexible stem. One is a rigid stem and another is flexible stem. A rigid stem means the stem which is fixed, it cannot move. I have shown in one diagram which is a rigid. So, here this is a rigid stem, one side is fixed. So, another is a rotation which is the which is not rigid and which we have fabricated in the double tune for that stem is not rigid, there it can flexibility is there. So, because you have fixed the both lower and upper tuning fork with a micro bridge. Okay. So, in both the cases it is simulated. Now, the fabrication, mask layout and fabrication, and there are 5 masks required for that. One is for electrode patterning, when electrodes are used chromium gold. Second mask is controlled etching for micro bridges, because micro bridge is not fully etched, control amount of flexure thickness you have to give. So, if you use 500 micrometer the quartz crystal of 500 micrometer thickness, so micro bridge is of the order of say 20 to 30 micrometer, that means it is told control etching of the micro bridges. So, so thin you can make, so that the structure will be stable as well as the energy will be transferred from upper tines to the lower tines. The desired energy which is out of plane vibration will be transferred, depends on how thin you can make the micro bridges. Okay. Third is the deep micromachining. Deep micromachining means releasing the tuning fork structure, because from the silicon, not silicon, quartz substrate you have to release the tuning fork structure, maximum portion you will completely dissolve, so that you will get that structure, that is the deep micromachining, quartz micromachining. Silicon tub formation, so that is for separating each of the sensor from other. Mask 5 is silicon tensile mask for electrodes over micro bridges. So, here you can see there is a problem, even you go for planar electrode, not sidewall, but if you make the electrodes, you can see next diagram I will show you that at the bridges there is a large step, because at the micro bridge thickness is very small of the order of 20, 30 or 40 micrometer, where at other places the thickness is nearly 500 micrometer of quartz. So, 500 it will go down, then the electrode will move. So, that means because of that large step, the metallization or metal lines fabrication cannot be done normal planar technology. You have to have a special technique for making electrode which will run over the micro bridge and the support stem. So, for that a tensile mask has been made, and using the vacuum masking which we call is a just the evaporation of material through the tensile, which will deposit as per the electrode structure, that is used. That means in that case you do not have to go for lithography. So, that vacuum masking technique using tensile mask has been developed in our laboratory, and we made the electrodes nicely over the microbead as well as the tuning fork surface. Now, what are the steps? Deep micromachining of quartz substrate, Z-cut quartz is written, that micromachining of quartz has to be standardized. Photolithography for electrode patterning is one important issue. Shadow evaporation on microbeads through silicon tensile mask, which I call is a vacuum masking, because it is done in vacuum machine, that is why we call it vacuum masking, not lithography. Lithography is done normal atmospheric pressure, and this shadow evaporation on microbeads is done in vacuum machine itself using tensile mask. Then chromium gold metallization, and the last is a test packaging and bonding. These are the steps we have to standardize for fabrication of these quartz gyros. And the anisotropic etching for quartz is different from silicon, and we use hydrofluoric acid, ammonium fluoride and water for etching quartz, micromachining quartz, and etch rate of quartz in that solution at 22 degrees C is 6 micron per hour, and at 80 degrees C obviously etch rate will be higher, 16 micron per hour. For patterning the chromium gold, we have to search for chromium etchant and gold etchant also. For chromium etchant, we can use ceric ammonium nitrate plus perchloric acid plus water. This is the etchant for chromium, which is used for proper adhesion of the gold film with the quartz. And for gold etchant, we use standard iodine based gold etchant from a renowned company from USA, Transient, they sell it. It is not cyanide based etchant, but it is iodine based etchant. Cyanide based gold etchants are not advisable to use in laboratory, because that is highly poisonous, you know. That is why some other form of etchant, gold etchants are available, which standard etchant solution you can use, and for that etch rate is at 22 degrees C, means room temperature, is 0.1 micron per minute. But one issue is important there, a removal of kinks to get vertical sidewall. So, that I think you remember in quartz micromachining class I told you, in a quartz micromachining the problem is the formation of the kinks, and then kinks can be removed by etching at a low temperature for long time, and certain chemical composition is to be changed in order to avoid the formation of the kinks. So, now these are the various etching solutions which are used for making the structure. Now, in this diagram you can see how the electrodes are coming. You can see this is some sort of the picture we have taken from the quartz itself. These are to support, you can see here. This is one support and this is another support, okay. And now the planar electrodes we are using. So, electrodes are, you see, the one will be positive, another will be negative. So, these are metal lines, one, this is metal line. So, these are metal lines are connecting, but you have to drive how, because this will vibrate. You cannot have the bonding pad on the upper tine. Bonding pad one is here, another is here. These two are bonding pad. So, now these two bonding pad, if you apply to amplify the electrical signal, so this will vibrate, okay. Now, through the bonding pad, you see it is going down, because this is a step, and then this is a microbead, it is running through the microbead, then it is going here, then it is going in the surface of the tines. Similarly, from the bonding pad it is going down, because the microbead thickness is very less compared to the bulk. So, here you can thickness you can see is a 500 micrometer, but here thickness is only say 30, 40 or 50 micrometer. So, it will goes down, then it runs here, then travels through this, then it goes here. So, in that way this one, and this is another for bottom electrode also, you can have the bonding pads here. All bonding pads are formed at the support frame, so that easily you can sense and and drive the electrode. This is the electrode pattern for force vibration, this one in this axis, but here the sensing electrode pattern is here for tuning from second. So, in this way electrodes are formed which will run over uneven surfaces, and that unevenness is huge. So, this kind of metal pattern you cannot make using normal photolithography process. Okay. So, for normal photolithography process, substrate surface should be planar. In VLSI, this surface is not exactly planar, but this up and down is not that much like here. Maybe 1, 2 or 3 micron difference of the surface evenness is there. Windows and the passivated the oxide, but here is of the order of say more than 300-400 micrometer steps are available in this case. So, that is not possible using normal lithography. Okay. Now, this kind of structure we made in our laboratory, and that is shown in the next V graph. Here you can see the quartz which is transparent, and the golden colors are the electrode, how the electrodes are just moving from this is the upper at one tine, this is another tine, this is a support in the bottom and support in the top, these two are support. Okay. So, this is the support frame is one here, and this is another support frame. This is the one tines, this is one tines, and this is the second tines on top and bottom. So, electrodes are running there. So, two photograph is shown, and here by because the picture you cannot say see where the electrodes are coming here. The reason is that if you take photograph, so there are two different planes. So, separation between the top plane and bottom plane is about say more than 300-400 micrometer. So, both the planes cannot be focused simultaneously. That is why you cannot see the golden line here, but some shadow things you can see it. This side, this and this in the same plane, but this particular zone and this zone there is a step of more than 300-400 micrometer. So, both the planes together you cannot focus it in microscope. That is why you cannot see here and here, but in rest of the portion which are in the same plane you can see the metal lines. So, this is the fabricated the gyro chip, and next question is mounting is very difficult. So, you can fabricate it, then mounting and testing, here comes the problem people facing lot of problem, and even now we are trying our best to characterize that using certain facilities, and we are running to different places for accessing their facilities. One facility is such facility available with the Space Research Organization, and the characterization of these sensors are not complete. That is why I cannot show you in the characterization curve here at the moment. So, after fabrication we are in the process of the packaging, this mounting in a test fixture, and the testing and characterization of the chip, so that we can get some idea about its sensitivity and what is its frequency change due to the rotation. Vibration change means some frequency change also will be there, and that characterization is yet to be done. Okay. So, just in this lecture I gave you certain ideas of the gyro sensors, different class of gyro sensors, silicon and quartz both, and some idea regarding how it is fabricated. Okay. There are lot of recent gyros are coming, which some of the picture I showed you, that is the comb line gyros, and another is the rotation wheel gyros. Those are really complicated. Fabrication process is also not that much easy. So, that you can just go through if somebody wants to take up these activities in your project work or maybe further research work. So, let me stop here. Thank you very much. Today we will discuss on a very interesting topic, that is MEMS for space applications. Already we discussed on the accelerometer as well as gyro chip, which are also used in spacecraft technology, but topic which I will discuss today is only meant for satellites. Positioning a satellite in a particular orbit is an important issue. So, how the MEMS devices is playing an important role for satellite positioning, that is the topic of discussion in today's lecture. You know, whatever the either aeroplane or satellite or the missile, whatever you are going to send in space, one of the major concern is the weight. So, miniaturization is one of the important issue. Miniaturization of the devices and different components is one of the major issue when you are going to integrate them either in a spacecraft or aeroplane or missile, wherever it is. So, the weight and small weight, miniature size is the issue, and you know MEMS will give you a process or a technology where you can miniaturize the devices as much as possible with lot of micromechanical action also. So, today we will discuss on micro thrusters, which are basically used for picosatellite program. Microsatellite and picosatellite is a topic of research today in many of the advanced level institutions around the globe. So, Indian Space Research Organization ISRO is also thinking in near future for microsatellite or picosatellite program. So, they have initiated an R&D effort to miniaturize different components and to get highly reliable, space qualified, small mass and small size devices, which may be helpful for reducing the weight of the space vehicle.